I'm going to speak today about the slow bond effect, and when a single slow bond may or may not affect the macroscopic behavior of a given system. So let's start with a somewhat standard model, probably the most simple case of this with a slow bond. Let's consider the symmetric exclusion process on dimension 1 with a slow bond. Here, Tn denotes the one-dimensional descriptors. Do you see my pointer, my mouse here? You can see it or not?
Yes.
Okay,
That's okay.
Thank you. So Tn is the notation for the descriptors in the circle with endpoints, or it can be Z as well. The point here is to be one-dimensional. So let's define the symmetric exclusion process with a slow bond. Eta T is going to will be denote the Markov process. In each site, we allow at most one particle, 0 or one particle. So, for instance, -4, there is a particle. So eta 0 is here is time 0. So eta 0 of -4 is 1. Eta 0 of -3 is 0, and so on. Okay. It represents a configuration of particles where at the most one particle is allowed per site. To each edge of its graph, we attach a Poisson point process. Okay, so time goes downwards, and to each bond we attach a Poisson point process. All Poisson point process have parameter 1, except a special bond, the slow bond, which has parameter alpha divided by n to the beta. Okay, so alpha and beta here are positive parameters. So as n increases, this parameter goes to 0. It means that this Poisson point process has less marks than others. Okay, so its parameter is smaller, so it has, in average, much less marks than others. And the dynamics goes as follows. When we find a mark, we interchange the values, the occupation values, at the vertex of the corresponding bond. For instance, here in the first mark here, when you reach this times go downwards. When we find the mark, we interchange values, but both values here are 0, so both sides are empty, so nothing happens. Okay? Please, any question, you can write the chat. I'm seeing it right now, so any question, you can stop me, please. At the next mark here, now we have a site is occupied and the other side is empty, so a particle jumps from one side to the other. Okay, and this defines dynamics, or in the descriptors, or in Z. In Z, it's necessary to speak about the Harris construction, but it works. And keep in mind that this slow bond, this special bond, special in blue, this special bond, decreases the passage of particles across it. Okay, so it's from where the name is slow bond. Is that clear? Any question about the dynamics? Okay, so it's a Markov process. Then let's define now the spatial density of particles, okay, of the system. So the empirical measure, which characterizes the spatial density of particles, how particles are spread in space, is defined by this so-called PNT, is defined as follows. In each site where there is a particle, we put a delta of Dirac. Okay, so you see here, we have this eta of x can be 0 or 1. There is particle, there is no particle. If there is a particle, it's 1, so it counts a delta of Dirac at that point. And let's note two things. First is the time scaling is Tn squared, so-called diffusive scaling. Okay, so we are seeing the system in the n squared time. So we have to give time the system to evolve. And the space is x over n. It means you are seeing the discrete torus embedded on the continuous torus. Okay, or if you work on z, you are embedding z in the real line by dividing it by n. So the distance between sites are taken as 1 over n. Okay, so this guy is the time scaling, this guy is the space scaling. Okay, so I'm not going to precise in which paper there is a part of the next result, but a piece of it are in all these 3 papers with Claude in 2010 and with Patricia Gonçalves and Adriana Neumann in 2013 and 2015. So assume that at initial time, so at initial P0, at initial time, the spatial density of particles converges in some sense to gamma. Then at time t, this converges to rho of tu, a function of space-time, where rho is. If beta is between 0 and 1, the limit is the solution of the heat equation, which would be the same limit as if there was no slow bond. It means the passage of particles across the slow bond goes to 0, but it's not enough to have any macroscopic effect. The same limit as if there was no slow bond. It's not strong enough to make any macroscopic change. On the other hand, if beta is equal to 1, the limit is the solution of the heat equation with these Robin boundary conditions or mixed boundary conditions. So you see the derivative at the side derivatives are equal, and they are equal to alpha times the size of the jump. We are going to have a jump at 0, a discontinuity. This low bond creates a discontinuity, and the derivatives, which means the flux of particles, is proportional to alpha times the difference of the densities, which is related to Fourier laws, or in particle systems, Fick's law. Okay, the passage of the quantity is proportional to the difference of densities. Okay, and if beta is bigger than 1, the limit is the heat equation with Neumann boundary condition. It means that's completely blocked. Nothing passes through. The slow bond is so strong here in this regime, so nothing passes through the slow bond in the limit. Okay, in this discrete system, always there is eventually some particle may cross it, but in the limit there is no pass of particles. That's the meaning of the Neumann boundary condition. Derivatives equal to 0. The flux is 0. Nothing passes. Okay. Before continuing, let me discuss why does the transition occur at beta equal to 1. Why is this value so special in the diffusive scaling? So an intuition goes as follows. In the diffusive scale, n squared, a round walk can travel the square root of its time. So a round walk walks the square of n squared, the square root of n squared. So round walk it will be spread in a box of size n. So if you have a box, here's the slow bond. Let's decide when, in which situation the round walk will be able to cross the slow bond. And let's see, n squared is the time. Here's the time. 1 over n is the fraction of this time the slow bond, the round walk spends close to the slow bond in this site. And alpha divided by n to the beta is the rate at which it crosses the slow bond. So this is of order constant if beta is equal to 1. So that's why beta equal to 1 is so special. Any question? That's okay. It's just an intuition, but it gives the idea why beta equal to 1 is important. Okay. So in this scale, the round walk will be able to cross a positive amount of times the slow bond. Okay, if beta is smaller than 1, it's going to cross infinite times. It means the density will be continuous at that point. So we have no discontinuity. Okay. After speaking about the law of large numbers, the previous result was the hydrodynamic limit. It's a kind of law of large numbers. So it's natural to speak about another kind of results. Interesting one, which is not from probability, it's from analysis, but it's related to particle system, is the following. Let rho alpha be solution of the case beta equal to 1. Okay, this is the same PDE with beta equal to 1. It's missing alpha everywhere. Here's alpha everywhere. Sorry, alpha in the rho alpha solution of this. Diffusive is the name for n squared. when the space is scaled by n, 1 over n, and the times is n squared. It's just that's a name for it. Okay. So and if you take alpha going to infinity or to 0, we may recover the solutions of the two previous PDEs. You see, from the PDE, the limit PDE partial differential equation in the case beta equal to 1, it depends on alpha. And if you take this alpha going to plus infinity or minus infinity, you may recover. And this result is only about PDE. It's not easy because it depends, have no explicit solution of this guy. But it relies on some Sobolev estimates, which comes from the particle system. And with Sobolev estimates, have a bound Sobolev norm, you may apply the Hellich-Kondratyov theorem, so can prove it. It's interesting. Have it in some sense the same transition in the macro picture. So let's speak about the central limit theorem, which equilibrium fluctuations. Fluctuations is the naming in particle systems for the central limit theorem. So in this situation, to state the limit, the boundary conditions are encoded in the space of test functions. So let's define the state of space test functions. As beta is, if beta is between 0 and 1, the usual Schwarz space of smooth functions decaying very fast, infinity faster than any polynomial. If beta is equal to 1, it's almost yes. No, sorry, are the torus, but yeah, the process is the torus, but the PDEs are in 0, 1. But 0 is connected to 1. It's a PDE in the torus with some boundary condition in the torus. Okay, but it's possible to prove it in if you consider the system in contact reservoirs, there is a work of Adriana, Baldasso, with slow boundary, with the limit is in the 0, 1. Yeah, the continuous torus. Here is the continuous torus, but it works. There is a paper also what you asked. Thank you very much, Marcel. So if beta is between so if beta is equal to 1, it's almost the Schwarz space, but to have the same boundary condition, the side derivatives are equal to the alpha times the size of the jump. And if beta is bigger than 1, the space is almost Schwarz space, but have side derivatives equal to 0. And the fluctuations, equilibrium fluctuations, it means we start the system from the stationary measure, which is Bernoulli everywhere of a constant parameter. So YNT is the density field, is the version of the empirical measure suitable for the central limit theorem. Instead of 1 over n, you have 1 divided by square root of n, and you have this bar here. This bar, it means the centered random variable. So I have to be tracking the expectation. So this guy, looking this guy as in the topological duo of S beta, like in the space of distributions, but duo of this space. It's a Frechet space, so it's duo. It converts distribution to solution of this PDE. It means it's a generalized Orton-Uhlenbeck process, where YT is space-time noise of unit variance, and the delta beta and nabla beta are the operators Laplacian and nabla, but in this domain. So the way to encode the phase transition is to put it on the space of test functions, and this implies that the correlations in each case depends on in those PDs, the corresponding PD. Okay, this is the central limit theorem. The trick here is to put the boundary conditions on the space of test functions. Any questions? Sorry, I was not fast. Okay. So large deviations. I have worked with Adriana in 2017, and non-equilibrium fluctuations out of equilibrium with Dirk Erhard, Patricia, Adriana, and Tavares. Mariana Tavares is she's my former PhD student. So let's speak about higher dimensions. But so far, I have spoken only about one-dimensional models. This one-dimensional model. So let's speak about higher dimensions. Okay, any question so far? Okay. Let's consider the following model. We have this lambda. Lambda is a region on the continuous torus, okay, with a smooth boundary. So N minus 1 TDN is the discrete torus embedded on the continuous torus. Okay, but this region here is defined on the continuous torus. And the rates, which you define as low bonds, are alpha divided by n to the beta, as before, if the extremes of the bond are in different regions, falling in different regions. Or if one vertex is in lambda and the other vertex is the complement, or vice versa. Okay, for instance, this guy is a slow bond. One vertex is inside the region and the other vertex is outside the region. Okay, as well, many others, all these bonds are slow bonds. Okay, so have a kind of surface of slow bonds, a slow membrane. Okay. To state the result, we need to define the normal exterior unitary vector. So give a point u in the boundary of lambda. Okay, and lambda is region the continuous torus. Okay, it's not discrete, it's continuous. So if u belongs to the boundary of lambda, zeta of u denotes the normal exterior unitary vector. Okay, at that point. So let's see the result. With Mariana in 2019, prove the following. Assume, as before, that the initial time the spatial density of particles converges to something, to a profile gamma. Then at time t, the system in the diffusive scaling converges to, if beta is between 0 and 1, the weak solution of the heat equation, as expected. Okay, the same as before. If beta is equal to 1, the limit is the weak solution of a heat equation with a Robin boundary condition along the boundary of lambda. But now you have this special factor here. You see, have these directional derivatives in the direction of the normal exterior unitary vector. Here and here they are equal. The u plus u minus is the limit from outside of or from inside the region. Okay, they are equal to alpha times the difference of density, the size of the discontinuity, time this factor. And you see, it's an interesting point. This factor is the sum of the modulus of the inner products of the normal exterior vector if each vector of the canonical base. So it means that the graph, the underlying graph, has an implication the limit. You see, it appears the limit. You have not only the dimension d here, but you have this product, the sum of these inner products here. So it depends how. It means also that the system is not translation rotating variant. If the position, the relative position between the lambda and the graph, in the case the discrete torus, is important. If you change this relative position, the PD changes, which does not occur in the subcritical case or in the supercritical case. In supercritical case is again this is the Neumann heat equation with Neumann boundary condition. You see, so the version, the dimensional version of the heat equation with Neumann boundary condition along the boundary of lambda. Okay, so have this interest behavior here, which depends on the relative position of the graph, the relative position of the surface with respect to the graph. Okay, I'm too fast. That's fine. Okay, I'm going well. Okay, so far I have spoken about particle systems, but what about a single particle? To our surprise, we searched in the literature for the limit of a Runge-Walker with slow bond. You couldn't find anything about the Runge-Walker with slow bond. Okay, so let's speak now about the Runge-Walker with a slow bond, which means which is the exclusion process with a single particle. Okay. So the model is the following: we have the continuous Runge-Walker on Z, and you have this special bond which whose parameters are alpha divided by 2 times n to the power beta, and ever else has rate to 1/2. The 1/2 here, the factor 1/2, this 2 everywhere, is just to have to put the process in the standard limit to the Brown motion. Okay, but it's the same with this 2 or without this 2. We are in continuous time. Okay, and this special bond, this low bond, is located close to the origin. So if my colleague Dirk Erhard and Diogo Soares da Silva, my former PhD student in 2020, we showed that this low bound run walk convergence distribution tool. So what's this n to -1 the power times the position of slow bond? Recall the position of slow bond is an integer. Okay, it's a run walk on Z. So this is the usual scaling towards the Brown motion. Okay, so it's the same if you take, for instance, Tn and you divide by square root of n, the same. You wrote it in this way, but it's the same. The usual scaling towards the Brown motion. So this low bound run walk convergence distribution 2. If beta is between 0 and 1, the usual Brown motion. Okay, so the slow bond is not enough to make any change. And I'm speaking here about a functional central limit theory. Okay, it's the limit as a run function, as a trajectory. Okay, so if beta is smaller than 1, as expect, is the Brown motion. Okay, this rate goes to 0, but it's not enough to cause any macroscopic effect. If beta is equal to 1, the limit is the snapping out Brown motion of parameter 2 alpha. I'm going to explain a moment what does it mean. Okay, what it means. And if beta is bigger than 1, it converts to reflect the Brown motion. Okay, observe that it's not immediate that the limit is the Brown motion even for beta equal to 0, because I have this alpha here. So even for beta equal to 0, there is some work to prove that the limit is the Brown motion. Okay, but it's the usual Brown motion. And what is the snapping Brown motion? Snapping out Brown motion. It's called the SNOB. Snapping out Brown motion. The SNOB is a recent process, Brown type process, constructed by Antoine Leger in 2016. It's a very recent process. It can be defined as follows. It's a process on one-dimensional process. On the positive half line, it behaves as the Brown motion. On the negative half line, it behaves as the usual Brown motion, but at 0 have some special behavior. Okay, it's not always the SNOB crosses the 0, but to cross the 0, have to follow this rule. First of all, we toss an exponential random variable independent of the process of the Brown motion of parameter 2 alpha. Okay. Then once the local time of the Brown motion on the positive half line on 0, okay, once the local time of the Brown motion at 0 reaches this exponential variable, this exponential random variable, then it changes of half line. He switch the regions. If it is in the positive, it changes to the positive. Okay, but it touches 0 many times, and this is increased the local time. Once the local time reaches this exponential value, it changes of a half line of region. Okay, this is the in words the meaning of the snapping out Brown motion. And this is the limit for the slow bound random walk. Okay. Let's speak now about non-symmetric models. All previous results, they were about symmetric models, the exclusion process with a slow bond, the low bond run walk, higher dimensions, but they are all in some sense symmetric. When you attach the slow rates to a bond, it makes the system symmetric in some sense. Okay, so let's see non-symmetric models. let's speak about the weakly symmetric extrusion process with a slow bond. Okay, so here we have a drift everywhere. It's given by this A divided by 2 times n to the gamma. Okay, and this plus to the right and minus to the left. Okay, so I have a drift everywhere. The whole system has a drift to the right. Okay, particles want to go to the right. And you have this special bond, as before, this slow bond, where it's not half plus or minus the drift. It's alpha divided by 2 times n to the beta, plus to the right and minus to the left. Okay. And with Patricio Gonçalves and Marielle Simon, 2016, we studied the fluctuations of this model. And the fluctuations, they have a lot of cases here. You see, first of all, this is gamma, this is beta. Okay, gamma is the drift, the global drift to the right, and beta is the strength of the slow bond. And there is nothing here because here the rates would be negative. Okay, you have this minus here, so you cannot not allow beta to be bigger than gamma, otherwise we'll have negative rates. It doesn't make sense. Okay, so it's only above the diagonal. So if gamma is equal to 1/2, we show that the limit is given by Stochastic-Burg's equation, which lies in the KPZ regime. And the other cases are all Ornstein-Uhlenbeck process in the gray region with no boundary condition, with beta is equal to 1, this strong line, black line here is if you Robin boundary condition, and the dotted region is with Neumann boundary condition. And this special point, this triple point here, is also Ornstein-Uhlenbeck process of Robin boundary condition, and stronger noise, have a stronger noise at this precise point here, when beta is equal to 1 and gamma equal to 1 is equal to 1. Okay, this is the picture of the fluctuations in the weakly symmetric extrusion process with a slow bond. Here there is a competition between the drift to the right and the strength of the slow bond to block the system. Okay. Let's pick any question. Is that fine? Okay. So let's speak a little bit about totally symmetric models. Curiously, they are older than the symmetric models. In 2001, Timo Sepalainen worked with the TASEP, the totally symmetric exclusion process with a slow bond. And it's interesting. In the totally symmetric case, you don't have to, there's no need to rescale the slow bond. All the particles are traveling to the right. Okay, so if there is an accident on the road, it's enough to cause a traffic jam. The rate slow bond is just smaller. It's not necessary to take it to 0. Okay, it's just smaller than the other rates. And Landin in 96 worked with the zero range process with slow bonds and also with slow particles, or slow bonds, or some particles are slower than the others. Okay. Okay, let me speak about now the extrusion process with a slow site, not a slow bond, a slow site. Before the slow thing was attached to the bond, but now would it be the same with a slow site? The point here is that the problem is completely different. It's interesting. I think for a long time, myself, Schutz, and Patricio conjecture that the limit should be the same as the slow bond, but it seems it's not. Okay, so in fact the invariant measure here is not the same. In this case, the invariant measure concentrates probability. This special site is almost all time occupied. It remains occupied for almost all times as n goes to infinity. So it's a trap. Okay, so the behavior here is completely different. The definition is almost the same, but the behavior is completely different. It's a trap. In 2016, with Patricia and Gunther, We studied the dynamic limit fluctuations of the system. It's not the techniques are a little bit different here, and you could prove that the limit is normal. It means it's blocked for beta bigger than 1, but you couldn't reach anything about the subcritical case, neither about the critical case, beta equal to 1. It's a very challenging problem here. I think there is much to study yet about this kind of thing, this kind of homogeneity. Currently, we are working with Chicheng Xu, Rodrigo Marinho, he's Patricia's PhD student, and Linji Zhang. I have some previous results. In resume, it seems it's periodic for beta smaller than 1, and non-linear, and it has non-linear boundary conditions for beta equal to 1. Surprising, it's a surprising thing. We believe the boundary conditions are non-linear for beta equal to 1. This is completely different. In the previous case, for slow bond, all the boundary conditions were linear. Okay, the phi derivative is equal alpha times a difference. That's linear. So we really believe that in this case it's non-linear. I think we are almost there. It's a very challenging problem. So, any questions? Okay. Some open questions have this low bound effect for other particle systems. For instance, in 2017, I studied the Kipnis-Marchiori result, but it's a very starting paper. There is much to do, a lot of things to study. How this low bound affects other systems than the exclusion systems. Have these low sites, very challenging problem, and possible connections with the Bouchot trap model. The low site is a trap. So how does it connect with the Bouchot trap model? Maybe about aging. I don't know. There is a lot to do. You have this low boundary case. I did speak about it. The first paper is from Baldass, Venezes, Neumann, Souza in 2017. With the dynamic limit of this low boundary, where the extremes of the box are connected to some reservoirs, and the exchange of particles with these reservoirs are slowed by a factor n to the beta, etc., etc. And relate to open questions. With Patricia and Adriana, we studied the fluctuations for this low boundary. Have also this long range exclusion process with low bound. This is a current work of Pedro Cardoso, my former master student. He's in Lisbon, working. He's doing his PhD with Patricia Gonçalves at this moment. I think I was a little bit fast, so I have a lot of time. I was worried because we started a little bit late, so okay, I ran a little bit. But we have plenty of time for questions and what you want. Okay, so thank you very much for all. It's special to the organizer for making it happen.